going to talk about a little review of the history of voltage standards. And basically, I talk about the latest generation of Josephson voltage standard. So this is the outline for the first part. The second part will be given by Stéphane Salvet. I will do a quick history review of the Josephson voltage standards over time, talk more about the programmable Josephson voltage standard, we call it in short PJVS, and the Josephson Arbitrary Waveform Synthesizer, JAWS. The slides will be about the quantum voltage requirements, what is needed to make a standard works, and finally discuss a little bit more the applications. So let's look back in time. For most of last century and for doing basically the start, all the voltage calibration were made with artifact. And those artifacts were Western cells, so a little battery cell with 1.018 volt. With the big drawback is comparing those cells from lab to lab, given any better accuracy than 10 to minus 5. But thankfully, in 1960s happened a new effect discovered by Brian Josephson, who actually celebrated more or less his 6th-year discovery of this effect last year. And what is the Josephson effect? It's a theory to describe the superconducting tunneling properties between two superconductors that are separated by a weak link. That could be a normal barrier, that could be insulators, and that's what defines Josephson junctions. So what Brian Josephson did, he did some calculation, or not calculation, did some theory, expressed that in terms of a microscopic wave function and with an amplitude and a phase. And he derived two very important equations. And the second one, the second equation, basically is linking the properties of the supercurrent flowing to the junction, to the voltage across the junction. And that's what we use as a metrologist, is basically this proportionality between the frequency we apply and the voltage we receive. And that is done by fundamental constant of nature, h over 2e. So with that effect in place, it was a good start to make standard out of it. And initially, they were done at really low voltage, about 10 millivolt, using single junctions. You can see there, made of lead oxide. And with that, they were able to reach 10 millivolt. And with this 10 millivolt, using some potentiometric and option to basically scale up to a larger voltage. In 1984, they start making more and more junctions, refine also the microwave distributions. And this is the first 1 volt SIS array in 1984, also made with lead alloy junctions. Finally, in 1990s is those array reached 10 volt. And one of the big advantage was the material used was using niobium aluminum oxide for the junctions, which unlike the 1984 version, you can use it more than one cool down and was able to survive multiple thermal cycling. So if you're curious about, it's a very brief review of those Josephson voltage over time. If you're more interested, you can just go in your browser and type NIST history quantum voltage, and there will be many, many pages describing all those different standards over time if you're curious. Now, how did the agreement evolve with time? We started with Western cells, and as I mentioned earlier, we're in the 10 to minus 5 level. And with the first junction, there was already a 2 order of magnitude improvement in the agreement between two different labs or two different systems. And finally, with the first arrays, the conventional array, the agreement went to the 10 to the minus 9. It was probably limited the way that the conventional array is hysteretic, so there's step jump, and there's also some effect like this. But with the arrival of the PJVS, which is programmable, now we have some intrinsically accurate voltages, and the agreement went down up to 3 part 10 to the minus 11. As you know, since 2019, now the Josephson effect is the primary realization of the SI volt, which all electricians are very happy with H over E that been fixed. And if you want to learn more about that, if you have not already, there's a nice mise en pratique about the definition here. And the point I want to mention here, so H and E are fixed, but those are two numbers, and the ratio we need to use is basically 15 digit. This is the recommended value from the mise en pratique. So let's go to Josephson voltage standard in general. The effect is small. So we have about, each junction provide about 2 microvolts per gigahertz. So if you have a single junction, you bias it at 20 gigahertz, you only 40 microvolts. The voltage we want to achieve, or practical voltage we want to achieve, is about 10 volt. So the only option is to basically have multiple junctions in series. And in this case, we can multiply the voltage. The other problem we can have here is the homogeneity of your junctions. So if you look at those curves here, they 3 different IV curves, 3 different type of junctions. They all give an accurate voltage here. And however, if you look the black curve or the green curve, they do not have a common bias. So we can only bias here the red curve. So in order to have the standards, you need a long array of uniform junction with excellent microwave designs. So here is why it took many years to develop all those devices from the discovery from Josephson. So how does the programmable Josephson voltage standard works is basically we have this long array. This long array is basically biased by RF signals, radio frequency signals, and then is subdivided in segments. At NIST, we prefer to divide it ternary, so with a factor of 3 function between those segments up to a certain point, and then we just have larger number of junctions just to add the voltage. In this particular case, if you use the ternary function, you can use the 3 levels of the Josephson basically IV curves, and you can decide to bias on the positive step, on the 0 step, or the negative step. Assuming you want the voltage generated by 2 junctions, that could be done by 3 junctions here, minus 1 junction bias here, and you have 2 junctions. Let's review a little bit of the technology that's available right now to achieve 10 volt. And there is like 3 different devices that are commonly used in laboratories. The first one is from NMIJ AST, which has the largest number of junctions, about 1 million junctions, slightly over 1 million junctions. NIST using about 250,000, and PTB technology transfer to Supracon has about 70,000 junctions. The main difference is the bias frequency from 70, 18, and typically 16 gigahertz. All of them use SNS junctions, so non-hysteretic junction. And the material used is different also between NMIJ and NIST and PTB. So NMIJ use niobium nitride and titanium nitride barriers, which has the great advantage to operate at higher temperature. So the device needs only to be cool below 11 Kelvin to operate, while the NIST and PTB technology use the niobium silicide junctions, and you need to operate below 5 Kelvin typically. To have this high density of junctions, there is one way to increase, is not just to make meanders across the device, but also to stack them vertically. And that's what PTB did it with double stack to basically double the voltage here. I didn't mention it, but can go to 20 volt. Or NIST use 3 to reach 10 volt, and NMIJ use 2 stack here. And finally, each device has slightly different properties, including the resolution you can reach. But the minimum voltage you can reach is relatively is small, but not infinitesimally small. So Eventually, if you go low voltage, you'll be limited here by increment about to 145 for PTB or 227 microvolts. Let's talk about the JAWS, the Josephson Arbitrary Waveform Synthesizer. This is a pulse-driven system. So the idea is we're going to send a current pulse to the junction, and the junction will basically rotate this phase by 2 pi, and at the output, we'll have here a quantized voltage pulse, where the area under the pulse is quantized on over h over 2e. So in order to do waveform, we just need to program or generate this pulse pattern here to make basically voltage pulses at the output. And the sequence determines the waveform. And this pulse repetition rate is typically in a gigapulse per seconds. And so yes, the same thing as for the PJVS, you need long arrays in order to have the right voltage. So in practical, we have those long array here. We want to save the number of pulse bias drive. So what we came up with, like for the PJVS as well, from dividers here to basically bring those pulses to 4 arrays here at the same times. You can see it here on the chip, 1 microwave input launch to 4 different arrays. And to reach a 4 volt, we need actually 16 arrays that are connected in series. And yeah, this is the way we can basically pile up the voltage and increase the voltage for the JAWS as well. And here is shown how it is implemented on the Cryocooler. And it's actually the system used for AC power at NIST Gettysburg. Let's talk briefly about the requirements. So the first thing, it's valid for both for the PJVS and JAWS. We need equipment, and the equipment in very rough line, you need cryogenic environment. The junction will not work at room temperature yet. We need a bias electronics for all the current source to bias the chip. We need the RF and pulse synthesizer, depending if you use a continuous wave for the PJVS or a pulse pattern for the JAWS. We need a DVM and a digitizer, depending on, to verify the properties at the output of the array. And obviously we need a cryo package. And it may be trivial, but if you want the actual voltage to be known, you need to know how many junctions you have on your device. So basically the junction count is very important in that case. For the operation, which will be mostly done by software, is to tune those bias parameters and verify it, and verify that you operate on the quantum regime. And finally, for the application, what you want to do, you want to run some calibration with your device. And also during that step, we want to verify the quantum locking range. In terms of requirement, we want the frequency to be linked to the SI, and that's why we need a traceable reference for the pulse synthesizer or the CW generator. But also we need to know that the frequency generated by the generator is correct. If that's not the case, then we don't have a quantum standard, or we're not traceable quantum standard. The second thing is to verify the quantum locking range. There is 2 states to operate a quantum standard. It's either in its quantum state or not. And that's the verification we need to do. And I put 2 arrows here because yes, we can tune the device by itself, have nice performance, and then we connect our equipment here to some applications, and we have a different circuit. And in particular case, the circuit itself can generate noise or other issues. So the best practice will be to verify the quantum locking range while operating the device. An example is, for instance, if we calibrate 2 Zeners, we put in a series opposition with the array with a null meter in between, we can just vary a little bit the bias current in the PJVS side and be sure that voltmeters stay around 0 volt. and see that there is no effect by changing this titer by 2 quantities. So a little bit plus, a little bit minus. If all results agree, then you are guaranteed that your system in a quantum locking range. And finally, there is some systematic errors. And we'll describe a little bit, but the systematic error can happen at every levels. An example of systematic errors we can have with the hardware will be leakage. Another for the applications would be, for instance, if you change the impedance of your circuits and you drive current. So all of those systematic error happens at all 3 levels. So to operate the JVS, especially the PJVS, we need, the first step is to provide what we call the margins table. That means that for each individual junction to measure which current we need to bias it. And we do it both on the positive and on the negative step. The reason for that, you just want to verify that it's symmetric. And the next step is to verify the width of each bias step to be sure that we can operate it safely. And if you have all this table then been built, the next step is to verify it. And that's what we do typically with biasing all the segments in series and opposition. And with that, we obtain exactly 0 volt. And by putting 0 volt, you can verify with great precision vertically that your array is quantized. There is no corners and there is no roundings and so on. I like to do an analogy with a road width for 2 reasons. The first reason is we want to automate our system. And now we've come in an age where both the cars are becoming electric. It's exciting, but also can self-drive. And it's definitely easier to have self-driving function on a highway than there is walking on a small gateway on a lake. So this is the first analogy for automation. It's much easier if we have larger operating range or larger QLR. The second thing is perturbations. If you're driving on the highway with a very wide road, if you have side winds coming in, you're not going to be really impacted there. Very unlikely here. Here you may have to hold your hands on the railings to not be falling on the water. So this will be more the analogy of running a system manually compared to automated. Now, if you have very, very small quantum locking range, I guarantee you that if there's a single perturbation here, you'll be on the ground. So no quantum locking range. So this is why it's important to get this vision of operating safely your device. Remember, a JVS or a quantum system can either be working or not working. So we want to be sure we have enough room here to make it work. So how do we visualize those quantum locking range? We can do it in terms of the bias current, in terms of the bias frequency, for instance, or the microwave power. And that could be done simultaneously. And what you can see, the goal of this image is there is a zone, there's a parameter range where you can operate your device. And everywhere here, it is safe, as long as you don't go too close to the edges. So that will be your road in a weird way, based on the 2 parameters. And we can do that the same way with temperature. And an important value here we can see on the Cryocooler, we can raise the temperature. So we define the table, measure it here. It's actually at 425 Kelvin. Here is shown the offset. And now we can increase the voltage by, the temperature by about 0.6 Kelvin up to that point here before losing quantizations. Here is a couple examples of systematic errors. One of them will be thermal EMF on the output leads. They can either be large because we choose the wrong materials, or they can be unstable because we have a bad connection or some problem with temperature fluctuations. We can also pick up noise or ground loop that can affect measurements. And there's also leakage current to earth ground and leakage current between the output leads that create some errors. So those ones, we developed recently at NIST new method to do it automatically. And this is now built up in our system to basically evaluate those systematic errors. So it's not just a guessing game. Briefly, before going to the applications, I would like to mention two types of noise we see in wave junctions. So here's like a traditional IV curves. And what noise can we obtain? We can have voltage noise. A voltage noise can happen, for instance, if you use RF synthesizer with a lot of phase noise. So in average, the frequency is right, but the frequency basically fluctuates a little bit around the average value. So that will generate a voltage swing here. So typically that's not the end of a deal, because if you have some noise, you can average it, assuming you do an Alain variance and you know what range you can operate and do the averaging. Another aspect that could produce some voltage noise if you have a resistive contact in your output leads, and that can also create some voltage noise. More dangerous for us is current noise, and that is basically if you have some AC perturbation coupling into your device, and the junction will see a little bit of AC current. This little AC current on top of your DC current for the bias would actually make the junction create some extra rounding here. That means that your quantum locking range here is reduced. It's not as long as expected before. So this is another reason when you do your measurements with the system by itself, and then you connect your measurement circuit, could be measuring in voltmeter or Zener or any other devices, that if you do that to verify the quantum locking range while doing the measurements. Another good example will be if you measure the quantum locking range, for instance, with a cable balance, because now you have a large apparatus that's actually connected to your JVS array. So these are the things that could happen, and we want to be sure that we remain quantized during the measurements to avoid any surprise. In terms of the applications, the first application, the PJVS, was actually for cable balances. And the main reason for that was the array were limited in voltage. And so they needed to wait for 10 volt, basically to calibrate more or less the Zeners that were available. Obviously, we can do voltmeter directly in calibrators. Now changing color to orange for AC, my coding here will be for AC applications. So you can also calibrate AC sources, having a 7 volt RMS output, but we cannot do direct RMS synthesis. So you cannot use a stepwise waveform generated by a PJVS and say, here, this is an accurate RMS source. It is not. There will always be a large systematic. So we try to avoid that. And instead, we basically take the portion of the waveform, which is fully stabilized on the step or quantized, and we remove the transient. Now, there's another type of measurement will be with impedance bridge. Those one use a square wave that minimize the role of the transient. Doesn't eliminate it completely, but those impedance bridge have some useful application in metrology. Although right now, most of those, the latest development have been done now with JAWS impedance bridges. There is the electrical triangle and current source. Try to close the triangle with a CT pump or other current source, Programable effect, and PJVS to make it close the triangle. And there's also other new applications, and I would like to show you or just mention two that we saw at CPM in 2022 in New Zealand. One was about adding a JVS chip on a cryogenic optical power calorimeters. And those calorimeters use basically an optical to electrical substitution method by adding, they already use the cryogenic device by just adding the PJVS on the cryostat, didn't add much, but simplify their traceability in order to do the electrical substitution. Another example was from Louis Palafox of using penning traps Penning traps needed an 80 volt voltage reference for their very precise measurements. And in order to do that, then we developed another tool made of 4 20-volt chips to reach that level. So there's always new application that comes up with JVS in general. If you want to have a little review of not the latest, but at least up to 2018, there is a review paper there that you can double check. And for JAWS, we have pretty much the same kind of landscape of applications, slightly different. JAWS was used for just noise thermometry as the reference for this noise waveform. Instead of Zeners, there is TVCs. Although there's a catch here, because the two don't generally like to talk to each other directly. So we need to find a measurement method to basically transfer the accuracy from JAWS to the TVC. And the reason for that is JAWS cannot basically drive a low impedance. They're not current source, they're just voltage reference, and TVC wants the current to operate. So we need to use buffer transconductance or some kind of a bridge to operate TVCs. But as for the PJVS, voltmeter, AC source, electrical power standard, impedance bridge, and other new applications, certainly welcome. And one of them here to finish the circles is at NIST, we really focus on developing RF applications. And currently, that seems like a small step. So right now we have a -48 dBm reference at 3 gigahertz using a JAWS chip. And but that's a field that we'd like to push forwards for new applications. And one of the main motivation is now our superconductive electronic group, where quantum voltage group in Boulder is part of it, is now in the CTL, or Communication Technology Laboratory. We are now in the RF technology division. So we have now nice colleagues we can talk to and develop application for that field. I think with that, it's going to be time to give the microphone to Stefan. And but before that, I would like to thank all the team in Boulder. So this is a composite. There are people that are still there. Some have left. But I'd like to thank everybody for the great support and all the work they've done. There. Thank you.